सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics, and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Radioactive Community Radio, Bengaluru.
एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज, की आवाज।
Latest information on STEM popularization.
Magnetic stress as a new SUFA of metal insulator transition. The mystery behind the peculiar metal insulator transition exhibited by certain materials under external stimuli such as temperature, pressure, electric fields has been decoded by scientists, paving the way towards designing functional materials and devices like sensors and actuators. Materials primarily exist in one of the two fundamental electronic states, metallic or insulating. However, certain materials exhibit the remarkable ability to transition between these two states under external stimuli such as temperature, pressure, electric field, and more. Since the initial discovery of this phenomenon in magnetite in 1939, the transition between metal insulator phase MIT has continued to captivate generations of scientists and engineers. Their foray into this area has offered critical scientific insights and application in various devices, and at the same time brought in the necessity of new materials that can exhibit metal insulator phase transition for industrial applications. Chromium nitrate is an example of such material, wherein the metal insulator transition is anticipated to be instigated by an unconventional force arising from the anisotrophic magnetic stress. However, the mechanism remained experimentally unverified even with the theoretical prediction for nearly 2 decades. A team from Jawaharlal Nehru Center for Advanced Scientific Research, JNCASR, an autonomous institute of Department of Science and Technology, DST, has experimentally demonstrated that magnetic stress that stems from the peculiar arrangement of atomic spin drives the simultaneous structural magnetic and metal insulator transition. The team led by Professor Bivas Saha has experimentally demonstrated the presence of magnetic stress as a driving force behind the metal insulator transition in chromium nitrate and illuminated pathways for its manipulation. The magnetic stress within chromium nitrate emerges from the interplay between two distinct magnetic orderings along mutually perpendicular direction directly tied to the magnetic exchange interaction between two neighboring chromium atoms. The team employed a technique that involves altering the equilibrium atomic spacing within chromium nitrate ultra-thin films to fine-tune the magnetic exchange interaction. Epitaxial strain engineering. When subjected to compressive strain, the magnetic stress increases, resulting in metal insulator transition at elevated temperatures compared to bulk value. Conversely, when the film is under tensile stress, the magnetic stress diminishes, prompting a metal insulator transition at significantly lower temperature than the bulk value.
Now, our next segment is Analyst in STEM.
Today we are with Dr. N.S. Vidhyadhiraj, Professor and Dean, Fellowships and Extensions, Theoretical Science Unit, Jawaharlal Nehru Center for Advanced Scientific Research.
So I work in the field of, as I said, theoretical condensed matter physics. Specifically, I work with strongly correlated electron systems. And to introduce the field, I will start with something contrasting. So Bangalore is called the Silicon Valley.
Yes.
Right? And silicon is at the heart of all our electronic devices because it's built, silicon is basically used to build all the CPUs, all the chips and so on. So the reason silicon is a semiconductor, if you see it from the physics point of view, is actually the reason comes from quantum mechanics. And the quantum mechanics of single particle, single electrons actually explains the semiconducting behavior of silicon very well. So silicon that way is a very conventional material because it can be understood using single particle theories. However, there have been thousands of materials known where single particle theories, where particles do not interact with each other, in these materials, it turns out the behavior of those materials is completely non-conventional. Okay? They don't behave like conventional semiconductors, they don't behave like conventional metals. So if you say, when I'm talking about conventional metals, I'm talking about gold, silver, copper, these are conventional metals. Conventional semiconductors means I'm talking about silicon, germanium, gallium arsenide, these are all conventional semiconductors. So these new kind of materials behave totally differently as compared to the conventional metals and semiconductors. How do they behave so differently? So to tell you how differently they behave, let me tell you another example. You have seen a single ant moving on the, let's say, on the ground. Okay? By looking at a single ant moving on the ground, can you imagine that a collection of thousands of ants can actually build an anthill without having a leader? Right? That is called an emergent property. When collection of large number of simple individual entities gives rise to very complex collective behavior, right? Okay. So similarly, if bird flocks, when a single bird is moving through the sky, you cannot imagine that when thousands of birds come in, they will form complex patterns, right? Yeah. And those complex patterns can actually be understood by very simple interactions between the birds. Right? It's not that the birds are communicating or doing a very complex communication to make that complex pattern. It's very simple rules of communication which helps them to make those very large complex patterns, which is dynamically changing also. Mm-hmm. Right? And there are multiple examples of such emergent behavior in the world. Yeah. Right? Mm-hmm. Our own consciousness, how life emerges, and consciousness itself is actually an emergent property. Okay. How we think, for example, just putting neurons together and our thoughts emerging from that collection of neurons is an emergent property. Okay. Similarly, electrons in a material, when they start interacting with each other, they can give rise to very, very complex electronic behavior. Phenomena like superconductivity. Okay. Where electrons, which are supposed to be negatively charged and repel each other, they actually pair up, attract each other, forming Cooper pairs, and give rise to a superconductor. Okay. Which is used in magnetic resonance imaging, which is used in brain imaging, all kinds of very interesting applications. Yeah. So superconductivity is one such application that we study. We also study things like metal insulator transitions. How by applying a small amount of pressure, material can transform from an insulator to a metal or from a metal to insulator. Again, because the electrons are very strongly interacting, and actually the system is sitting at the edge of some phase transition. Mm-hmm. And by pushing the system a little bit, either through pressure or doping or magnetic field, you can push the system from one phase to another phase. Okay. And this is technologically extremely useful because you can use it to build exceptionally sensitive sensors. Okay. By applying a small amount of stress, you are changing the system's property drastically, which can be measured, and that way you can actually recover what was the applied stress, right? So similarly, for sensing extremely tiny magnetic fields, for example, our brain produces very tiny magnetic fields. If you want to sense that, you really need something which is so sensitive that by applying a small magnetic field, you can push the system over the edge, right? That is what strongly correlated systems offer. Okay. An exceptionally sensitive phase diagram, very rich phase diagram, where metal insulator transitions can happen, magnetic transitions can happen, superconductivity transitions can happen. So this is a whole new area where electron-electron interactions dominate over single particle theories, single particle kinetic energies, okay, and gives rise to new emergent exotic phenomena, right? So that's basically the area of research.
Okay, sir. Thank you. That was very brief and
Sorry,
very
it was too
understandable.
long.
No, it was very understandable actually. How was your research beneficial to a common man or India as a whole? And what kind of contribution is it making to the field of science in India?
So I use certain techniques in my research,
Okay.
which are based on quantum many-body theory. And to tell you frankly, my area of research does not have any direct applications in the industry.
Okay.
However, our research helps people who are in material science and modeling these materials to find the best models that can represent the behavior of these materials. For example, when Intel uses silicon for making a chip, right? Intel has to know exactly how silicon will behave when you dope boron or phosphorus into it,
Okay.
right? Or when they make it into a nanoscale device like a transistor, then Intel has to know how this material will behave when you make the bulk silicon crystal into a nano-sized transistor, right? Those studies have been already done, and they were done sometime in 70s and 80s, and that has gone into all this fabrication business. To understand how these materials behave at different scales, different temperatures, different conditions. The same thing does not hold true for the kind of materials that I work with.
Okay.
Right? We do not have such detailed models. We do not even understand why these materials behave the way they behave. Right? So my work actually goes into theoretically understanding and computationally understanding why these materials behave the way they do, using techniques of quantum many-body theory. So it's more of fundamental science right now, but eventually it's a futuristic work, and eventually in the span of about 10 to 15 years, when devices will start getting made using these materials, people will start using our models and our techniques. So that's the contribution.
Okay, sir. So could you brief about your past, present and future works?
Well, I have been working in the field of strongly correlated electron systems, but in JNCASR, we actually get to collaborate a lot with experimentalists. Okay. So I have had very fruitful collaborations in JNC. In fact, when I joined JNC, I started working with Professor K.S. Narayan, who works with polymers, and he works with organic electronics. So all the electronics, most of the electronics that we use today is based on brittle materials like silicon, right? And you know that if you drop a mobile phone, it will break, right? But imagine a mobile phone that will not break. In fact, it can bend, right? That is only possible if you have some kind of flexible electronics. And polymers offer such possibilities, right? You can have flexible electronics. So Professor Narayan actually works with these organic polymers which are conducting and can be made semi-conducting as well as conducting, and using those he is able to make flexible devices, wearable devices, flexible solar panels, flexible displays, right? All of this is possible. So when I joined JNC, I started working with him. Even though the techniques that are needed for studying those materials is very different from what I use in my core area, I was able to contribute meaningfully and understand what is going on in, for example, a position sensing device made out of this organic material. And then I collaborated with another experimentalist where he was in sort of close to my area of research, but still somewhat different. And in their experiments, they were seeing some very unusual observations which could not be explained using existing theories. So when I worked with him, then we developed a theory which was able to explain what was going on in their system. And that was very satisfying, right? So, and more recently, I've been working with Professor Kulkarni, where he's been looking at neuromorphic devices. It's a very exciting, new area where people are trying to mimic, natural intelligence by building networks of neurons, right? But these neurons are nothing like what we have in our brain. These neurons that we are looking at are made of inorganic materials, and which can be developed in a lab, right? Which need not be grown in a biological process. It can be, developed and made and fabricated in a lab. So these neurons, if you put and the kind of new computing paradigms. So I've also started looking at things like quantum computing.
Okay.
One of my students is in IBM currently. So he is the head of quantum AI division,
Okay.
and he had also done a workshop here. So we are talking to him regarding quantum computing. So apart from conventional computing paradigm, which is the von Neumann architecture based computing paradigm, we are also looking into other computing paradigms like quantum computing, neuromorphic computing, along with experimentalists, but theory wise also.
Okay, sir. So do you have any idea about where India is right now ranked at in your field of research?
Yes, unfortunately it's not too high.
Okay.
See, experimental research in my field is actually very, very difficult because most of the research that happens in quantum many-body systems has to be done at very low temperatures.
Okay.
So, for example, you may know that quantum computing has to be done at millikelvin temperatures, which is like, if you look at it in Celsius, it's like minus 273 degrees Celsius, right?
Okay.
Nowhere on Earth you can find that. The lowest temperature on Earth may be somewhere close to minus 70, minus 80 degrees Celsius, right? So, in fact, even on Moon you will not find this. It's only inside the lab. On Earth we are actually able to produce millikelvin temperatures. So and having such refrigerators, these are called dilution refrigerators. These refrigerators can only be found in very few labs across the country. Plus, you need liquid helium for that. You have to maintain constant current, vibration free, all sorts of very stringent conditions.
Okay.
So it's very difficult to have experiments for doing these kind of systems, for understanding these kind of systems. So unfortunately we are not ranked very high in the world for these things, mainly because the experimental facilities are not so good. Theoretically also, what we see is that there is a dwindling number of researchers who are working in this area. Well, actually, I would attribute that to the growing ML and AI domain, which has been attracting a lot of very bright people out of the core physics areas, right? So, but India is doing reasonably well. Okay, I would say probably about 5th or 6th in the world in terms of number of publications, in terms of number of researchers, in terms of the quality of the output. So I would say it's somewhere like that.
It will be really helpful if you give some information about your contemporaries.
Yeah, so let me talk about a few contemporaries whom I have been associated with.
Okay.
Not contemporaries, but my mentors. I'll start with them.
Sure.
So I did my PhD with Professor H.R. Krishnamurthy in IISc, and my co-guide was Professor T.V. Ramakrishnan.
Okay.
So Professor T.V. Ramakrishnan has made very fundamental contributions in this area that I work in. And one of his papers turns out to be one of the most highly cited papers ever.
Okay.
And Professor H.R. Krishnamurthy has worked, he's in fact the student of a Nobel laureate, and the technique that he has worked on is used very heavily in the area that I work on. It's called numerical renormalization group.
Okay.
So so he was, and in fact Professor Krishnamurthy was one of the key players in extending a theory called dynamical mean field theory to a new domain of application by developing something called dynamical cluster approximation. Okay. So these may seem like technical terms, but it's important because if the dynamical mean field theory restricts you to a very small domain of application, in order to be able to apply to a larger domain, you need a non-trivial modification of the theory, which is what Professor H.R. Krishnamurthy actually helped in doing.
Okay.
Right? So that was about my mentors. Now about my contemporaries, I would say a lot of very nice work is being done. One of my contemporaries who is in IISr Kolkata, his name is Siddharth Lal.
Okay.
He has actually developed a new kind of renormalization group technique, called unitary renormalization group, which actually he has claimed that it overcomes many of the deficiencies of the numerical renormalization group that I told you my mentor had helped to implement, right? So it seems to be a revolutionary new technique which gets us access to even wave functions of many-body Hamiltonians and so on. So that's theory-wise, and there are many such contemporaries. I can talk about many such people. Experimentally also, I know there are many people who are doing great work. There's one person called Dr. Professor Yogesh in ISER Mohali who is doing extremely nice experiments, very difficult experiments on strongly correlated systems. There's a lady whom I'm collaborating with in ISER Trivandrum. Her name is Deepshikha Jaiswal Nagar. She's also doing beautiful experiments on single crystals of magnetic systems. And recently she has found a material which defies all conventional wisdom in the area of superconductivity, high TC superconductivity. Yeah, I can go on, and here also we have Professor Sundareshan, who is doing a lot of very nice work in multiferroics, magnetic systems, superconductivity. So yeah, I mean there are a lot of people who are doing very nice work.
Yeah. Okay, so how are Indian industries associating with your research project?
Currently, as I said, my area of research does not have a direct application.
Yeah.
Right. However, in the area of quantum computing, I think we may be able to establish some collaboration with IBM and other industries, where if we use the quantum anybody theory framework, we may be able to develop algorithms for solving quantum mechanical problems. In fact, if we actually, we are also in the process of developing some other methods which may be useful for companies which are trying to build software for understanding materials themselves. So there are actually lots of companies who are working with computational software, who are building computational software in order to investigate materials. Okay, they are into material science domain. Now we think that the method that we are developing may actually be a very radical departure from the conventional methods used, and it will help them to overcome many of the limitations that are presently there in the formalism. So, but that is in the near future. It's not at present. So we are working towards that. So, but currently I'm not interfacing with an industry.
Here we are, signing off. Stay tuned with us to catch up on the latest science updates and learn about STEM experts.